This is Math 251, and we're looking at section 11.9. We're going to be talking about a few different things here in terms of vector-valued functions. We'll look at the unit tangent and unit normal vectors first, and then we'll take a look at curvature and components of acceleration. So starting with the unit tangent and unit normal. We actually already have talked about the unit tangent, so you really already know what it is, right? The unit tangent vector would be the tangent vector, which is the derivative, divided by its own magnitude in order to make it a unit vector. So my unit tangent vector, if I write down a definition, here's my curve r of t. The unit tangent, capital T of t, will be first of all the derivative. That's how we make a tangent. And then we divide by the magnitude of the derivative in order to make it into a unit vector. So I now have a tangent vector of length 1. So on my curve right here, I would have this tangent vector of length 1, and that would be my unit tangent. All right, what about the unit normal vector? Well, the unit normal vector is actually just the perpendicular to the unit tangent pointing inward. So on my picture, the unit normal vector would look like this. It's also going to have magnitude 1, just like the unit tangent did. It's going to be perpendicular to the unit tangent. And there are actually two perpendiculars here, right? One goes this way, one goes that way. But the unit tangent, capital N, will always define as the one that points inward. All right, how do we find the unit normal vector? Turns out, in a way very symmetric to this, to get the unit normal vector, we take the derivative of the unit tangent vector. And again, it has to be length 1. So we'll divide by the magnitude of t prime. All right, let's take a look at an example. I would like to find general formulas for the unit tangent and unit normal vectors given the curve r of t equals t comma t squared. Now that's a pretty simple function, right? That's just a parabola, parameterized. X equals t and y equals t squared. In fact, if you look toward the bottom of the page, you'll see a graph of it. So a relatively simple and straightforward function. Let's go ahead and get the unit tangent vector first. R prime over the magnitude of R prime. So let's see, R prime would be 1 comma 2t. Over the magnitude, square root of 1 squared plus 2t squared. So I'm going to end up with 1 over the square root of 1 plus 4t squared and 2t over the square root of 1 plus 4t squared. Not too bad. The unit normal. This has to be t prime divided by the magnitude of t prime. And now all of a sudden I'm going to say, hold on a minute. This is looking a whole lot worse, right? I have to take the derivatives of these, which is going to be a little bit of a mess in and of themselves, and then I have to divide by the magnitude of that. In fact, this is a rather lengthy algebraic process. I'm actually going to do it off on a separate sheet of paper and then just write the answer in there. So let's go ahead and do this. First of all, I need t prime. Just simply because it's going to make my algebra easier later on, and I only know this because I've done this problem a lot. I'm going to keep the form that I have, and I'm essentially going to use a quotient rule on this. So let's see, quotient rule would be, just as a reminder in case you haven't done it for a while, it's gf prime minus fg prime over g squared, right? So let's see, we'd have the bottom, my g value, 1 plus 4t squared, times the derivative of the top, which is 0, minus the top, which is 1, times the derivative of the bottom. I'm going to think of that as 1/2 power, so 1/2 times 1 plus 4t squared to the negative 1/2 times 8t for the chain rule. And then it all goes over g squared. When I square that radical, I just get 1 plus 4t squared. Comma. Start a new line because that was pretty lengthy, and I'll have another one here. Same thing here. I take the denominator times the derivative of the top, which would be 2, minus the top, 2t, times the derivative of the denominator. Same as before. And once again, that all goes over g squared, which is 1 plus 4t squared. All right, let's get some... Oh, and by the way, all of that's just t prime. I still have to divide by the magnitude of all of that, which I'm going to do some simplifying before I try to deal with that. So for right now, I'll just put that magnitude of t prime down there, and we'll deal with it when we can. All right, let's see what we've got here. I'm going to see if I can do a little simplifying. Obviously, that's just 0. And I can reduce the 2 with the 8, make that a 4. So this is actually 4 over the square root of 1 plus 4t squared. Excuse me, it's negative 4t over that square root. And then this 1 plus 4t squared in the denominator, I'm just going to write that as multiplying by the reciprocal of 1 plus 4t squared. Keeps things a little bit cleaner. Comma. Here I've got 2 times the square root of 1 plus 4t squared minus, get rid of those, and it looks like I'm going to have an 8t squared here over the square root of 1 plus 4t squared. Oh, oops. I almost forgot that denominator. Let's go back and pick that up. All of that would be times, and I'll write that again as times 1 over 1 plus 4t squared. All right, all of this still goes over the magnitude of t prime. So let's see what we've really got here. This would be negative 4t. And I can multiply these together. That's just a first power times a 1/2 power, which would give me the 3/2 power. Makes that one a little bit nicer. And over here, I think things would go a lot better if I could get a common denominator. So I'm going to go ahead and say, let's multiply just this term right here by the square root of 1 plus 4t squared over itself. So I get a common denominator with that one. And I'm just going to kind of write that in right here. When I do that, I'll keep this 2. And then multiplying those radicals together, I just get 1 plus 4t squared. And then I've got this minus 8t squared. And now both of those are over the square root of 1 plus 4t squared. All of that is multiplied by another 1 plus 4t squared. So actually I could do the same thing as I did here. Instead of the radical, why don't I just write that as the 3/2 power? All right, we're getting there. Oh, sorry, still divided by the magnitude of t prime. Haven't even touched that part yet. Okay, so I've got negative 4t over 1 plus 4t squared to the 3/2. And here I'm going to get a 2. And then notice I'll get an 8t squared and a minus 8t squared, so those terms will just cancel themselves out. And then I've got 1 plus 4t squared to the 3/2 in the denominator. That's about as simple as that's going to get. So let's go ahead now and start working on the magnitude that goes in the denominator. I have to divide by the square root of this squared plus that squared. When I square this, I'll get 16t squared over the square of that, which is just going to cancel out that denominator, 1 plus 4t squared to the 3rd power, plus, same denominator, so I'm making it all one fraction, and the square of that one would be 4. Okay, so let's see here. On the bottom, I'm going to notice that I could factor a 4 out of here and make that 4 times 4t squared plus 1. So in fact, I could cancel a factor of 4t squared plus 1 here. And so my denominator now is just the square root of 4 over 1 plus 4t squared squared. Well, that's a perfect square. So this denominator is really 2 over 1 plus 4t squared. And since that's in the denominator, I'm going to write it as times the reciprocal. And now let's see what we've got. That's going to become a negative 2t. And I'm dividing out a first power, so I'll just have that to the 1/2 power, or in other words, the square root of 1 plus 4t squared. Here, that becomes a 1 in the numerator. And same deal in the denominator, I'm just left with a 1/2 power, or a 1 plus 4t squared. All right, I think I finally got it. Now, keep in mind, that was a pretty simple function, right? All I started out with was a simple parabola, basically y equals x squared. And it took a lot of work to get to that point. Let's go ahead and put that in and take a look and see if hopefully we can maybe start seeing some shortcuts. So the result that we just got was negative 2t over the square root of 1 plus 4t squared and 1 over the square root of 1 plus 4t squared. If you take a look at that t and that n, I think you're going to see right away that there's a very clear relationship between them, right? The x value here just became the y value there, and the y value almost became the x value, but it did have the opposite sign. So I'm going to notice that if the unit tangent has form x of t, y of t, then at least in this example, the unit normal seems to have form. Let's see, the x became the second component, and the y became the first, and changed signs. Now I know that we only have one example to go with, but we probably don't want to do a bunch of these. As you saw, they're a big mess. And I'm going to tell you that this does hold true all the time. So the unit tangent usually isn't too bad to find. And typically, rather than go through that whole process that you just saw, we'll generally use this little cheat here to get our unit normal. This is going to be great, by the way, for two-dimensional vectors. When we get to 3 dimensions, though, it doesn't hold true anymore, so we'll talk a little bit about that a bit later. All right, before we leave these, let's go ahead and I'd like to find the unit tangent and unit normal vectors, specifically at t equals 0, draw them on the graph, and then the same thing at t equal 1. So let's start with t equals 0. First of all, notice that r of 0 would just be 0, 0 squared, or 0, 0. So let's see, I'll put these on the graph in pink. We're at the point 0, 0. T of 0, and I'm just using the t that we calculated here, plugging in 0 for t, would be 1 over the square root of 1 plus 0, and then 2 times 0 over the square root of 1 plus 0. And that's just 1, 0. So the unit tangent vector is the vector 1, 0. That should not surprise you at all, because of course it's supposed to be tangent to the graph and of length 1. So far at least we're seeing that what we think should happen happens. How about n of 0? Now I can formally plug in to the n that I got here, or I can just use this little relationship, which is faster, right? It says take this y value, make it the new x value, but opposite sign. Just for thoroughness, I'll put the negative there even though it's a 0. And then take the x value, make it the new y value. So we get 0, 1. Also not surprising, right? Our unit normal has to have length 1, and it has to be perpendicular to the unit tangent. So that's exactly what we would have expected to have gotten. Notice it does point inward into the interior of the curve. All right, what about at t equal 1? At t equal 1, first of all, r of 1 is 1, 1 squared, just 1, 1. R is the position function, so we're at the point 1, 1. The unit tangent vector, t of 1, just plugging into my t formula that I have at the top of the page, would be 1 over the square root of 1 plus 4, and 2 times 1 over the square root of 1 plus 4. So I've got 1 over the square root of 5 and 2 over the square root of 5. Just so that I can kind of guess where those will end up on the graph. What is that approximately? It's about 0.45, 0.9. So if I was going to try and draw the unit tangent, I'd go over 0.45 in the x direction and up 0.9 in the y direction. Maybe I'd end up about there. And notice just visually, that does look tangent to the graph, so far so good. What about n of 1? Again, I can actually plug in, or I can use the little trick. The x will be a negative 0.9 now, and the y will stay positive 0.45. And I'm going to apologize in advance for this one. Unfortunately, I've given us a non-square grid, so the perpendicularity that we're supposed to see, we're probably not going to see as well as we should, but we'll give ourselves the benefit of the doubt here. To graph this starting from the 0.11, I would go to the left 0.9 and up 0.45, maybe about there. And that would be the n. And again, these are actually perpendicular, and if I had been smart enough to give us a square grid to graph on, we would have seen that a lot better, so my apologies for that one. All right, well, as you can see, calculating n in particular is a really long and algebraically intense process, unless you happen to get lucky and have a function that works out really, really well. We do have a shortcut for two-dimensional vectors, but for three-dimensional vectors, we got nothing. We'd actually have to go through that whole process. It is so algebraically ugly that we'll usually end up just using a calculation device, in our case Maple, to do that work. And I'll be attaching a Maple video to this so you can see exactly what that looks like. In fact, I'll be redoing this problem on Maple. All right, so that's unit tangent and unit normal vectors. We'll come back in the next vector and talk about curvature.